Good day, students. Today's video is going to be on the epsilon delta that we normally use, or we could call it, this is how it's actually called. It's the precise definition of a limit. Now, I want to make this video as quick as I can, but with the greater understanding of why we do the precise definition of a limit, and then I'll definitely sneak in an example while we do that. Okay, so let's look at what it says actually. So what does it say? So the precise definition of a limit says that for every epsilon that is greater than 0, there will exist a certain delta that will also be greater than 0. So we're saying that both of them are positive. And then we'll say such that, and now we're going to say that 0 is less than the absolute value of x minus a, and is less than delta. And this will imply that we will then have, from this information, we will have the following as well. We will say that any function minus our limit value will be less than epsilon. Okay, now where does this come from? What we are trying to show you over here is this actually all comes from a certain limit. So let's say that we are given the limit as x approaches a from both sides, we can assume for now, of a function f of x, which will give us our limit value, if you can agree. Remember that we're going to have this limit of a function over here, and then if we plug in our a value into that function, or wherever x approaches, we'll get a certain value over here. So what we have over here is, sure, we have a proof over here, right? But how do we actually visualize all of this? So I'm going to give you a graph over here. So let's say that we have a Cartesian plane. I'm just going to make it like this. So we're going to have a y-axis here, and we are going to have a x-axis over here, right? Let's just say that this is going to be our Cartesian plane for now, only consisting of the positive and the so both positive y and x-axis. So we'll have the y-axis and we'll have the positive x-axis, right? Because we are sticking true to our definition over here. Okay, so let's say we have a random function, right? So I'm just going to create like maybe a root function, like that, and then it continues all the way to positive infinity. Okay, so what we need to consider is the information that we have over here, right? In the definition right here. So let's just focus on our limit for now. Remember, that's the first thing we would normally focus on. I should have written that one first, but it's absolutely fine. So what we are saying over here, right, is, so we are going to consider our x approaches a, right? And we know because it's x approaches a, we're going to see that it's in the x-axis, right? So our a value would lie on the x-axis. So let's just say that our a value will be somewhere, let's say, here. Okay. And then because of that, we'll get a certain output, which is our limit value. Am I right? Yes, I am. And then we are going to lead it all the way towards when it actually touches the function. So it's a vertical line all the way to that function point, to the coordinate on this function. And then the output value would be somewhere here, which would be L over here. Okay. It's not the straightest line, but it doesn't matter. I'm just trying to explain what do we do in these precision, the definition over here, the precise definition. Okay, so let's look back at our definition now. Now that we've put down points on the graph, we have this coordinate. You can also even say this is the coordinate A and L, but we're not going to focus on that right now. Okay, so we say over here that for every value where epsilon is going to be greater than 0, so meaning that it's going to be positive, there exists, so which means from our epsilon, there will then exist a delta, which we will determine in the long run, in our proof. There will exist a delta that is also greater than 0, meaning that it's positive. And now we say such that, then we have this x minus a, which actually our a value comes from our limit value over here, or our limit, sorry. And over here, this whole absolute value is going to be in between delta and 0. And because we have the absolute value, we know that the final answer will be positive. So that's what makes this first part true over here. This first part is going to be true because it is greater than 0. So that means we need to find a value that is between delta and 0. Okay, and then from this information that we have here in number 1, our number 2 over here needs to be true, or will be true when we are doing the proof. So first we're going to prove the first one, and then we're going to prove that the second one is correct. Okay, so from this point over here, we have the absolute value of f of x, which is our function, minus our limit value, which is going to be less than epsilon. Okay. And we know that this would actually also have to be greater than 0, because obviously our absolute value will eventually be a positive value. So that would also be something that we could add as well. Okay, so how do we know where epsilon is going to be and delta is going to be? Where is it going to be, in the y-axis or the x-axis? So how we actually know this is because we need to look at our absolute values, right? We know that f of x is an output value, and the limit value is also our output value. We know that the f of x is going to be equal to the L. Am I right? So over here, well, I mean, depending on your a value, obviously. Your f of x will give you an output of L depending on your a value. And over here, right, we can clearly see that epsilon falls under the output values. So therefore epsilon is going to be in the y-axis. And then therefore our delta, because it has x minus a, which would also fall under our x-axis, delta will be in our x-axis. So we're going to do the following. Because we want to prove that for every value of epsilon is greater than 0, then there will exist a delta. We're going to start with epsilon first. Okay, so let's just choose a random value. Let's say that, or a random place here. Let's say that epsilon is going to be somewhere here. So what I want to actually do is I want to actually make sure that this function goes something like this, so that I can actually link them together over here. So let's say that the epsilons must be the same, right? So just note that this distance, so let me do it in a different color here. We're going to see that this distance is going to be epsilon here, and then this distance over here is going to be epsilon. Notice how I'm saying distance, because distance plays a huge factor in our proof over here with the definition. Okay, now we're going from an output to an input, right? We can do that. We know from years of experience with functions that we can actually move from an output to an input value. So we're going to move this all the way here, and then we'll get a certain distance here, right? And then this will be all the way over here. Okay, so now what we need to do is the following. We know that epsilon is going to be here on the y-axis. So we can actually name this over here L plus epsilon, this point over here, right? And this will be L minus epsilon, this point over here. Because we are basically taking this L value and we are minusing it by the epsilons that I've written in red over here, and adding it by the epsilon that I've written in red. Okay, and then what we are going to be doing, right, is we are going to do the following over here. We can see that this distance, I'm also going to be doing this in red, is smaller than this distance over here, right? Visually we can see it. Now, the smallest distance, we will choose this as where our delta is going to be, right? We want to find a value that is a delta that is closer to the a value, and that is why we choose the smallest distance. Remember, that is mainly what our limit would say, so that we can have a true limit. Remember that the limit, we need, in order for a limit to be true, we should actually know the following, right? The limit as x approaches a from the left-hand side must be equal of a function must be equal to the limit as x approaches a from the right-hand side of that function. It must be the same, such that then therefore the limit will exist. And that is what we are doing with our delta. We want the distance of the delta to be the same. So what I'm going to be doing is I'm going to take this distance here, right? I'm going to copy this, and then I'm going to see where it is the same. So let's just do it like this. Okay, so now let's line that up over here. So around there, that is going to be our delta distance. So this would be our distance delta, and this would also be our distance delta. And we would know that this over here is going to be A plus delta, because it's going towards the right side over here. It's going to be going towards it's going to get larger basically when it goes right here. And then this value over here, I'm just going to do this actually. It's in black. This one is going to be A minus delta, which is that one over there. So we are disregarding this one for now. So we are going to find an epsilon over here such that we are going to manipulate this epsilon such that we are going to get this distance somewhere here. So we are going to find out over here, right, that what is our epsilon at this part over here. How is our epsilon manipulated such that we can get these deltas the same? Okay, now let's actually move to the proofs now. So from this definition, just to clarify some things over here, we've shown that for every value of epsilon greater than 0, over here we can see epsilon being greater than 0, there will exist a delta that is greater than 0. That is a part of our definition. And now we move on to the distances over here, saying that delta is in the x-axis and epsilon is in the y-axis. And now we just prove it we just show our work over here on the graph. And now we have to do our proofs in order to show that the limit is true by using our new information here, right? To prove that this distance is going to be given by how we manipulate our epsilon over here. Okay, and then we'll get some distance like this. Okay, now let's move on to the proof. I'm going to give a random example, and then that will be it for the video. Okay, so here is a linear equation, right, or a linear function that I'm going to give for this example. I'm not going to give such a hectic one for this one because, once again, this is an explanation. I want to now show you how we apply the proofs. So we can see that this over here is actually in the form of our limit as x approaches a, where our a value is going to be -2, and we have our function here. Our function is actually just 5x minus 2, which is equal to our limit value, where our limit value is equal to -12. Okay, so from this point over here, we are going to use the definition, okay? So just bear with me for now. We're going to use the definition. For every epsilon that is greater than 0, there will exist a certain delta that is also greater than 0, such that we will have 0 is less than the absolute value of our x minus our a value. And remember, if we're saying x minus a, we need to substitute our -2 in, right? So that is our a value, according to what I've said just now. So we're going to substitute -2. And then we're going to say that this is also less than our delta. Okay, and now this will tell us that 0 is less than our absolute value, or we don't have to include the 0 over here because we already know it's true. We're just trying to show something as little as possible from our definition here. That it's going to be our function, our f of x, which is going to be, I'm just going to put it in brackets, 5x minus 2, minus our L value, which is -12. Absolute value, which is less than our epsilon. All right, so the first thing we need to actually do is going to be the following. The first thing we need to do is literally just simplify it. So I'm just going to simplify it like this, right? So we know that the negative and a negative will just become a positive by now at this point. and we'll have x plus 2 in this absolute value. And then if we just write this down over here, let's just take these brackets away, this will become a positive, and it'll be 5x minus 2 plus 12. So negative 2 plus 12 is just going to be, or you can say it as 12 minus 2, which is just equal to positive 10. So it'll be plus 10. Okay, cool. And then let me just make it a little bit neat at this point here. And here we have it. Cool. So from this information, we need to do the following, right? We need to look at this. Sorry about that. Okay, so the first thing we're going to do is look at this, right? Over here. And the reason why I left this 0 less than is because it's not important in our proof. We know it's less than, going to be greater than 0, but let's just do the following, right? So we're going to take that and we're going to say the absolute value of 5x plus 10 is less than epsilon. What we are doing is we're going to try and manipulate our epsilon such that we can get this kind of something around what I've just did previously, so that we can get the two deltas in the same distance, basically, right? We can get the same distance for the two deltas, right? Okay, so what we are going to do here is we are just going to be doing inequalities. So we are going to obviously just simplify this over here, or we're going to use, we know that we can actually factor out 5, right? So if we take out 5 as a common factor, it's going to go outside of the absolute value, and that's going to be x plus 2 is going to be less than epsilon. And then over here, what we can do is we will divide both sides by 5, and then we'll get the following. It'll be x plus 2 is going to be less than our epsilon over 5. And now what we can see over here is that we have x plus 2. And where else do we have x plus 2? We have x plus 2 over here. And we know that the absolute value of x plus 2, is going to be less than our epsilon. And that is what we know. So therefore, because of that, we know that epsilon is less than delta over here, we can now choose our delta to be epsilon over 5. So if we were to manipulate the graph of epsilon from the longer distance, if we manipulate our epsilon and we divide it by 5, we will get this distance epsilon to be the same as the other distance, which I have gone through in the graphical example. Remember, this is not the same function as we used in the example in the beginning of the video. The beginning of the video, I wanted to use that example because it shows over here that because of this curve over here, we will have a difference in distance, and that's why we need to find our epsilon by using. We need to find our delta by manipulating epsilon. Okay, so what are we going to do by this point? What we are going to be doing by this point, sorry about that again. From this point, okay, so we had choose delta equal to epsilon over 5. So from this point, what we are going to be doing is we're actually going to be proving that this is in fact the same as that. Or we are going to prove this over here as well. So let me do that over there. From this point, we are going to be using this, right? And we're going to use algebra on this specific absolute value. So we have 5x plus 10. And I'm going to use it as an equation here. Or we're just using an algebraic expression here. This can be equal to 5x. So it's going to be, or we can take out the 5 as a common factor over here. I know we're doing it again, but once again, we are proving. Okay, and then from this point over here, we have 5 multiplied by x plus 2. And we know that x plus 2 is actually less than our delta. So we can say that this would be less than 5 multiplied by our delta. And the reason why we keep the 5 over here is because, let's say for example, right, if we have, let's say, a value, if we're saying that, let's say 4 is going to be less than 6, we know that this is going to be true. 6 is greater than 4. if we were to multiply both sides by 5, gonna keep it to this example here, we can see that this 5 times 4 is just going to be 20, and 5 times 6 is going to be 30, and it's going to be staying, it's still going to be greater than the other one, and that is why we use this over here, that inequality. Okay, let me actually keep this. And now from this, we know that this will actually just be equal to 5 multiplied by our epsilon over 5. Because remember, we've shown that we've chosen our delta to be epsilon over 5, right? So from this point, we know that the 5s can cancel out, and then therefore, we are left with epsilon. And then, okay, just because it's an equal sign over here, this is actually linked up to this part. All of these are just linked up into one, but this is just telling us that this is actually less than our epsilon. And that is our proof for delta epsilon. So we just work backwards basically to show that our epsilon is true when delta is going to be equal to epsilon over 5.